that we have some of our similar learning targets, still working to understand this value of e, which hopefully we feel comfortable with is approximately 2.718. We got that from our limit definition. Using notation with the base of e, that natural log is still going to come into play, and then also solving some application problems when we have a base e involved. So solving applications that have exponentials and logarithms. So to start, we have this compounding interest equation that's used when talking about investments and money. And we have some different pieces to it, some different numbers and values that we'll need to plug in for. So A stands for the amount after a certain time. All right, and then we have this P value. P stands for the principal, which is also known as the start value. So if we're talking about making an investment, this would be saying I invested $1,000. My p-value would be 1,000. The 1, hopefully you're okay with, is just 1. And then our r is going to be our rate, all right, our interest rate most often. And we're going to write this as a decimal. So if I had a 12% rate, I would write that as 0.12. Then we also have n, that's already written for us here. N is going to be our number of compounds per year. So for instance, the word annually would be once per year. Semi-annually would be twice per year. Quarterly, hopefully you're telling yourself, would be 4 times per year. Monthly, we feel good about the fact that there are 12 months in a year. And then daily, we're going to go with 365, although some banks only use 360 because of bank holidays where interest is not compounded. But anyway, those are going to be our common n values that we have. And then t, there was a t there. T is going to be our time. So how long are we letting this investment grow within our account that is giving us some interest rate paid back over that amount of time. So then this becomes interesting because we can compound interest, well, as often as we would like to. So ideally, the more often you compound the interest, the higher your money is growing. And we're going to do some comparisons of accounts over the next few days. But thinking about this little piece right here, 1 plus some fraction raised to the nth power, looks a lot like something we've looked at before with that number e. So I'm going to do some fancy math. I want you to try to pay close attention as I go through this. All right, and I'm going to do some manipulation to this formula. So the first thing I'm going to do is I'm going to just decide to call this variable x. X is going to be equal to n over r. So if you look at this part right here, ooh, those are close. How do r over n and n over r relate? Great, they're the reciprocal of each other. I totally agree. So the reciprocal of x is 1 over x, and I've made this substitution. Well then, I'm going to go ahead and I'm going to substitute in for this n value. To isolate n, I get x times r. I still have my t, I still have p, and I still have a. Now, looking even more closely at this part right here, this looks a lot like that definition of e that we had in our previous video. And if we think about the number of compounding or how often we are compounding, we could consider what happens when our number of compounds goes to infinity, in which case this value that's in brackets all turns into e, and I'm still left with r and t and p for my principal being equal to my present amount. Well, if this was really going to turn into e, that means x has to be going to infinity. So I would have taken the limit, in which case we are compounding interest, not daily, not even hourly, not even minutely or secondly or thousandth secondly. We are compounding continuously. Right when I was going to write a fancy word, of course my menus pop up. Continuously. When you compound continuously, you will use this equation that we refer to as PERT, because you are going to compound as often as possible. So, on the next page, at the top, you've got a place to write this compounding interest equation. We also want to write continuously, means we're talking about A equals PE to the RT. So, given $10,000 is invested at an interest rate of 3.2%, find the balance of an account after 10 years if it's compounded quarterly. All right, we can do this. We want to know the amount after 10 years. We've got an interest rate of 3.2% and our initial investment of $10,000. So 1 plus. My rate is 3.2%, but I've got to write it as a decimal. I'm compounding quarterly, so that's 4 times per year. So n is 4. And I'm doing that for 10 years. All right, so let's be careful in our calculator. I'm going to do this first part on the inside, parentheses first, following those order of operations. So parentheses, raised to the exponent, which is 40, times 10,000. Means I have $13,753.76. So now what if it was compounded monthly? Well, monthly, that means our 4 is going to change to a 12. Go ahead and take a second, pause your video, see if you can get your amount if you are compounding monthly. All right, so is it reasonable that if we compound more often, or 12 times per year, that we would end up with more money in our account? Hopefully you answered yes. So let's see what happens if we compound our interest continuously, which is something that actually happens in a lot of investment concepts, especially when calculating interest. So we're going to have our 10,000 e to the 0.032 times 10. So being very careful with my calculator, I'm going to start with my exponential part. So e to the 0.032 times 10. If you don't have the new calculator that shows this math type, you might have to put parentheses around your exponent. And then I'm going to multiply that by my 10,000. And I get 13,771 and some change. So definitely better to compound continuously because I'm going to make more money, which I think is the point when you're doing your investments. And so continuously compounding interest, again, it makes sense that you would earn more money after the same amount of time if you compounded your interest more often. So the key is the word continuously, means PERT. Everything else you got to figure out how many times per year am I compounding, and that replaces our n variable. All right, so another use for exponential equations is the concept of half-life. So let Q represent a mass in grams, so that's our amount, of radioactive radium, whose half-life is 1,599 years. The quantity of radium present after T years is given by this equation. So, find the initial quantity. Initial quantity. So, if we think about what the word initial means, initial would be when time is equal to 0. So, our quantity is 25 times 1/2 to the 0, because 0 over 1,599 is 0. Well, anything to the 0 is just 1. We learned that with our properties of exponents. So my initial quantity is equal to 25, which is also in place of P if we're talking about an investment or if we're talking about an exponential equation. Find the quantity after 1,000 years. So my quantity that I'm looking for after 1,000 years right? So I'm going to go ahead and put that into my calculator. Again, very carefully, I'm going to use 0.5 my 1/2, raised to the 1,000 divided by 1599 times 25. And I get 16.206. And that's going to be grams. Now, if we think about it, it takes 1,599 years to get to half of my quantity. Well, if I started with 25 grams, half would be 12.5. So after almost 1,600 years, I should be at 12.5 grams, which means after 1,000 years, which isn't quite that way yet, I still have more than that. All right, so when we work with these exponential equations, we really need to think about the reasonableness of our answers. This next one says when, so we're looking for a time t, will the quantity be 0 grams? Well, the quantity is going to be 0, t over 1599. Well, we learned back in our other videos that our exponential function has a horizontal asymptote at 0. In this case, we're talking about 1/2, which means we've got this reflection happening, still approaching 0, but since it's a horizontal asymptote, will we ever have 0 grams? And the answer is no. And that's one of those things about half-lives, and if you think about taking medicine that has a certain half-life, you are always carrying some very, very tiny percentage of it in your bloodstream. It's not going to get down to 0 grams if it only has a half-life. You're taking half of half of half of half, which is never going to be equal to 0. All right, last one. Students in a math class were given an exam and then retested monthly with an equivalent exam. What if I went back and gave you your Unit 4 exam? How do you think you would do? The average scores for the class are given by the human memory model, where t is the time in months. So, looking at this equation, we've got 3 questions to answer. And we're going to go with question 1 on the original exam. Well, if they're tested originally, that means that time t equals 0. So 78 minus 17 log of 0 plus 1. After 3 months, we're going to have log of 3 plus 1. And after 11 months, we're going to have log of 11 plus 1. So go ahead and take a second, and in your calculator, remember where that log button is, carefully enter in these 3 expressions, and let's see how the students did on the original, after 3 months, and after 11 months. All right, so average score originally was a 78, and then when they were tested again after 3 months, it dropped to a 67, and then after again 11 months, it dropped to a 61. So if we think about that log graph, right, in this human memory model, it's showing us that over time, humans, well, forget. So this is our intro into our application problems. We will be working with application problems pretty extensively throughout Unit 10, focusing especially on finance problems and solving for time t equals question mark. In this case, time was never going to be something we could solve for because there is no time at which our quantity would be 0. But if I changed that and I asked when would the quantity be, let's say 12.5, hopefully the answer you came up with is 1599 because that's half of 25. But I could also ask for when would the quantity be, let's say 3 grams. What would that look like? How long would that take? Or when would the quantity be 21 grams? What time or how long would that take? And that's going to be kind of what we work on solving over the next few videos. But important to remember these 2 equations, all of these different pieces and what your variables mean. And then specifically, whenever you see that word continuously, 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 you're going to switch and you're going to use PERT because you get that E value in there.